Hello, class. We're going to go ahead and get started on an online delivery here because of this is coronavirus forward statistics. So we're looking at section 6.1, which discusses discrete random variables. So really what a discrete random variable is it's just a way to name something and put it into a nice little package. So the ideas are the same, but we're now going to kind of package them and call them capital X. So let's discuss what we mean here, discrete random variables. Okay, so we're just going to call the random variable some numerical measure of an outcome, and we'll use this capital X here as all of the possibilities that it can take on. So we've got two kinds to look at. One is discrete, and discrete just means the same thing that it meant before, in that if you're looking at two particular values, you can always find two values for which there's no value between them. Whereas a continuous random variable is something that you can measure or that you could represent potentially as a decimal number. So a discrete is going to fall into a countable, and continuous is measured. Okay, so some examples, the number of light bulbs that burn out in the next year. If there's 10 light bulbs in the room, well, that's discrete because you could have either none of them burn out, so 0, only one of them, 2, and so on, but you would max out at 10 since there's only 10 light bulbs in the room. And if there was more than one, then there was at least 2. You can't have some value between 1 and 2 burn out. Same for the leaves, on number of leaves on an oak tree. So these are A and B are discrete examples. But if we measure the length of time between calls to 911, then that could be measured as finely as you wanted it, seconds, microseconds, and so on. And you could use a decimal number to measure the time between calls. Or the volume of a balloon could be measured, and that could be done. And ultimately, a decimal representation. So just think of a measurement, such as lengths or not quantities, but lengths and volumes, times, and then think of the numbers as the discrete. Okay. If we establish a probability distribution, then we've got all the possible values of a random variable and their corresponding probabilities. So usually we put those possible values, so little x, which is one of the possible outcomes of x, and then the probability of that little x goes over here. So let's say that we're doing the light bulbs. Remember, we had 0, and there were only 10 bulbs in the room. Just barely have enough space here to do this. But then if we measure the probabilities, let's say that the probability of 0 bulbs is pretty high. So let's look at that again. So number of light bulbs that burn out in the next year. So here's the 0, and here's if all of them burn out. Well, the probability of all of them burning out, maybe that's very low, so we might say something like 1% chance of all of them burning out. And the chance of all of them remaining for a year, maybe that's pretty high. Maybe that's something like 0.85. Okay, so here I've used up 0.86. So all the rest of that that means that the sum of all these has to be 0.14, because the sum of all the probabilities has to equal 1. Okay, so I'm not going to distribute and try and make up probabilities for each of these outcomes, but this represents a discrete probability distribution, and this is how we represent X. Capital X is the set of all possible outcomes, and little x is each individual outcome, and the probability of each little x is given in the corresponding row for little x. Okay, so now we've seen our first discrete probability distribution. Here's another one. We're going to call the random variable x the number of free throws scored out of 3 shots. Well, here's the distribution. You could make 0 of them, 1 of them, 2 of them, or 3 of them, and you can't make more than 3 because you only took 3 shots. And let's say that you're fairly decent at shooting free throws, then the probability of missing all of them is pretty low. And the probability of making only 1 is also pretty low. And your highest probability outcome is that you would make all 3. But again, if you tally and add up all of these results, you get 1.0 or 1, because one of these things has to happen. So when I tally them all together, I get a 100% chance that you either made 0, 1, 2, or 3. There are no other outcomes. Okay. So that's another example of a discrete probability distribution. Now, notice that our outcomes are discrete. There's no decimals here in the outcomes. Okay, so here's a couple of rules to get used to for probability distribution. We've already said that the sum of all the probabilities tallies up to 100% or 1. And if I look at any one probability, it could be 0 or between 0 and 1, or it could be 1. So 0 means there's no chance for that outcome. 1 means there's a 100% chance, and anything between 0 and 1 is the corresponding probability. So these are the 2 limitations on probability distribution. So if we were to ask if this table represents a probability distribution, all we have to do is make sure that these rules are followed. If I tally this, does it add up to 1? And are all of my outcomes between 0 and 1 inclusive? Well, we can see right away that part 2 is met, but we'd have to do a little adding up. And if you add this up, we fall short of 100%. So this is, no, doesn't represent a probability distribution. How about this one? Well, we don't have to think any further because that rules it out right there. There's no such thing as a negative. There's not such thing as a negative 0.01 chance of x becoming 5. It just doesn't exist in the real world. Okay, and so finally we're going to get to one that works out. All these are within the proper range, and if I tally them, I get 100%. Okay, and then we can also create this graph here, and let's say that our new random variable, so this is our capital X, is the number of weekdays a worker goes out for lunch. So number of weekdays a worker goes out for lunch is what we mean by capital X. Little x are the possibilities, possible outcomes. I could go to lunch 0 days in a week, 1, 2, 3, 4, or 5. But there are only 5 work days in a week, so that's where we have to stop. And each probability is corresponding probability. Most of the time they go out one day per week. And then we can create a table here that represents this probability distribution. And if we look at the shape of this distribution, this little question over here, a comment over here says, comment on the shape of the distribution. Would the empirical rule apply? And the answer is no, because it's not bell-shaped. This is a right-tailed. Okay. If I want to calculate the mean of a discrete random variable, I can actually take a look at this table and plug those values into this formula. So what is this saying? Well, this is just saying take X times its probability and add it to the next X times its probability and add it to the next X times its probability. So I'm summing the products of each row, and that gives me, that winds up calculating what we call mu of X. So if X is the number of days per week a worker goes to lunch, then I've created the average from this formula right here. Okay, so it summarizes right here for us what we're doing. We're just multiplying each value by its probability and adding them together, and we call that the expected value, and that's the same thing as the mean. Okay, so let's take a look at this particular. This is again the number of days a week the worker goes out for lunch, and we're just taking each outcome times its probability and adding the results together. And when we do the math, we find out that on average, a worker goes out 1.49 days per week. Well, that's interesting because there's no such thing as 1.49 days in a week. But if you average that out over a long period of time, you're able to get that 1.49, and it has meaning in that context. Okay. All right. Here's some randomly selected. So what we have here is a sample, and our size of our sample is n equals 100. So we've got some employees going out 3 days a week. They like to eat out. Some of them 0. They bring their lunch 4. Looks like most of them are in the 1 range, but this is from a sample, so this doesn't necessarily adhere to the probability distribution that it's a sample for. So let's look at the results. If I add up each of these cells and divide by the number of cells, which is 100, then I get 1.49. Okay, imagine if our sample was limited to the first 10 entries. Then when we calculated X bar, we get 1.3. When our sample is all 100, that's enough so that by the law of large numbers, we do a really good job of estimating the mean. Okay, so X bar is an estimate for mu. So X. Okay, so that's just a sample estimate. All right, so that brings back to mind the law of large numbers. Notice if we just do very few trials, we don't really hit the expected value. But if we increase the number of trials, we start to lie on the line that represents the expected value for that particular experiment, or in this case, discrete random variable. Okay, so the mean of the random variable represents what we would expect in the long run, so therefore we also call it E of X. So this is just the expected value of the random variable X. So that's another way of looking at mu of X is equal to E of X. Okay, so lastly, we're going to look at a life insurance policy, and it pays a beneficiary a certain sum of money upon the death of the policy holder. And the policies have premiums that must be paid annually. So let's say that they sell a $250,000 1-year term life insurance policy. So that means that if you die over the course of that year, then someone's going to receive $250,000 on your behalf. And they sell this to a 49-year-old female for $530. Okay, so the probability that a female of this age will survive the year is very high. It's calculated to be 0.99791. So we can use our average calculation to determine the expected value of this policy to the insurance company. So if they calculate the average, they want to come up with some profit, and then depending on, and they also want to ensure that they're putting two things together here. One is the law of large numbers. So they need to have enough, they need to cover enough people so that the law of large numbers guarantees them that they're going to make their expected value. And then we also have to use our calculation here for the expected value of the discrete random variable. So let's get back to this information. Okay, so if the person survives, then the company has kept their $530, and the chance of them surviving is this very high value. So we've got the 530 times the probability that they get $530 from that person with no payout. Now, if they don't survive, they still got the $530, but then they had to pay out the $250,000. So basically, we take that 530 and subtract what they had to pay out, and so we end up with this number right here. It cost them $249,470, slightly less than $250 because of the $530 that they received. And then the probability is 1 minus the chance that they survive. So we're going to take that amount and multiply it by that probability. And notice they come up with a positive value. Now that's not a lot of money if only one person is insured, but if we get the law of large numbers in place, then it does two things for us. Okay, does two things for us. It bumps the profit up to make so that $7.50 multiplied by thousands of insured people becomes the expected profit for that company. And then, of course, occasionally somebody's going to die and you have to pay out, but the probability is going to remain the same. Okay, now if I want to calculate the standard deviation of a discrete random variable from its table, I've got two options here, however you want to look at it. I'll take the sum of the individual value minus the mean for that random variable quantity squared, and then multiply it times the probability of that particular random variable. And then once I've summated all of that, I'm going to take the square root of that value. Okay, so what we like to do with these kind of formulas is build little tables with columns where we build the parts slowly, and then we'll summate the column and then take its square root. Okay, so x is the value of the random variable, and mu sub x is the mean of the random variable, just everything that we've discussed so far. So, remember the variance is just the square of the standard deviation. So this gives us both the standard deviation right off the bat, and then if I want the variance, well then I just won't take the square root, because the variance is the square of the standard deviation. Okay, so remember that the mean that we need that we found earlier was 1.49. So this is again the workers going to lunch number of days a week. So this is consistently 1.49. 0 minus 1.49 is negative 1.49. So the parts I need, I'm building as columns. And what I needed under the square root radical was x minus mu sub x squared times the probability of 0 or x. So these are all the parts, and this is the list that we're going to summate. So if I tally all that up, I get the 0.8699, and then I take the square root of that to get the standard deviation. So here's our standard deviation, and before I got its square root, I already had the variance. Okay, I'm going to go ahead and follow up here with an assignment for you online, and I'll see you next time.